Every technology you use today was built on the wreckage of something that did not work, not refined from something that partially worked, not improved from something that almost worked. Built from the ground up on the structural lessons of repeated, catastrophic, expensive, humiliating failure. This is the story of AI that nobody tells. Not the triumph of AlphaGo, not the wonder of ChatGPT, not the breathless headlines about superintelligence and existential risk. This is the story of the decades in between, the long silences, the abandoned laboratories, the careers that ended in obscurity, the funding that dried up, the promises that could not be kept, the winters. Because here is what the history of artificial intelligence actually teaches. If you are willing to look at it honestly, it teaches the same thing that the history of every great human achievement teaches, that the breakthroughs are not the story. The failures are the story. The breakthroughs are just what the failures eventually became. It begins, as most things in AI begin, with extraordinary optimism. The year is 1956, a summer workshop at Dartmouth College. 10 researchers gather for what they propose will be a 2-month project to solve the problem of machine intelligence. Among them, John McCarthy, who coined the term artificial intelligence; Marvin Minsky, who would go on to found MIT's AI laboratory; Claude Shannon, the father of information theory; Nathaniel Rochester, who designed IBM's first scientific calculator. These were not naive people. These were among the most rigorous, most capable minds of their generation. And they believed, with a confidence that in retrospect is almost painful to read, that the fundamental problems of artificial intelligence could be substantially solved within a single summer. They could not. Not within a summer. Not within a decade. Not within their lifetimes. But what they started that summer, the intellectual framework, the foundational questions, the community of researchers who would carry the work forward, would eventually lead, 66 years later, to the tools that now shape daily life for billions of people. The distance between those two things, the summer of 1956 and the world of 2022, is a distance measured not in years but in failures. The first major approach to AI was called symbolic AI, or sometimes good old-fashioned AI, a term coined by philosopher Hubert Dreyfus, who was also its most relentless critic. The idea was elegant. Intelligence in this view was fundamentally about symbol manipulation. The brain was essentially a sophisticated computer operating on symbolic representations of the world. If you could give a machine the right symbols and the right rules for manipulating them, it would think. Early successes seemed to confirm the approach. In 1956, Alan Newell and Herbert Simon built the Logic Theorist, a program that could prove mathematical theorems. In 1957, they built the General Problem Solver, which could solve a wide range of problems by searching through possibilities in a structured way. Simon, famously, predicted in 1965 that machines will be capable, within 20 years, of doing any work a man can do. He was wrong. Not slightly wrong. Not almost right. Comprehensively, systematically wrong, in ways that revealed something fundamental about the nature of intelligence that the symbolic approach had missed entirely. The problem was what researchers came to call the combinatorial explosion. Real-world problems do not have neat, finite solution spaces. They have possibility spaces so vast that even the most sophisticated symbol manipulation systems could not traverse them. Chess, seemingly a perfect domain for symbolic AI, had approximately 10 to the power of 47 possible game states. The symbolic AI systems of the 1960s could not search that space fast enough to play chess at any meaningful level, and real-world intelligence was not chess. It was infinitely more complex. In 1966, a report commissioned by the United States government, the ALPAC report, concluded that machine translation, one of the most ambitious early AI projects, was not only failing to deliver useful results, but was unlikely to do so in the foreseeable future. The report recommended cutting funding to machine translation research dramatically. It was the first of many such moments. The first time the gap between promise and reality became large enough that the people controlling resources, governments, universities, corporations, looked at what AI researchers had promised and what they had delivered, and decided the promises were not worth the investment. This is the first AI winter. Not a dramatic collapse. Not a sudden discovery that the whole project was misconceived. Just the slow withdrawal of funding, the closing of laboratories, the redirection of talent. A gradual cooling of the intellectual climate around a research program that had promised too much and delivered too little. The researchers who lived through it described it as a kind of institutional amnesia. The people who controlled funding did not know enough about the technical details to understand why progress was slow. They only knew it was slow. And slow, in the world of institutional science funding, is indistinguishable from wrong. But the work continued, quietly, in the margins. In the late 1950s and early 1960s, a psychologist named Frank Rosenblatt at Cornell University had been developing a different approach entirely. Not symbol manipulation, not logic. Something more closely modeled on the biology of the brain itself. He called it the perceptron. The perceptron was a simple mathematical model of a neuron, a unit that received inputs, applied weights to them, and produced an output. Train enough of these simple units on enough examples, Rosenblatt believed, and the system would learn to classify the world on its own. Not by following rules, by detecting patterns. The Navy funded the research. The New York Times ran an article in 1958 describing the perceptron as the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. And then, in 1969, mathematicians Marvin Minsky and Seymour Papert published a book called Perceptrons. In it, they demonstrated with rigorous mathematical proof that the perceptron could not learn certain fundamental types of patterns. It could not solve the XOR problem, a simple logical relationship that any child could grasp. Their conclusion was interpreted widely as a proof that the neural network approach to AI was fundamentally flawed. Funding dried up. Research programs closed. A generation of researchers abandoned the field. They were wrong to abandon it, but they would not know that for 20 years. The 1970s and 1980s brought a second wave of optimism, centered on a new approach called expert systems. The idea was different from symbolic AI's grand ambitions. Instead of building general intelligence, why not build narrow, highly specialized systems that encoded the knowledge of human experts in specific domains? A medical diagnosis system that embodied the diagnostic logic of the world's best physicians. A geological analysis system that could identify mineral deposits with the expertise of a master geologist. These systems worked. Within their narrow domains, they worked remarkably well. Mycin, developed at Stanford in the early 1970s, could diagnose bacterial infections and recommend antibiotic treatments with accuracy comparable to medical specialists. Dendril could identify organic molecular structures from mass spectrometry data. And once again, the optimism exceeded the reality. The problems with expert systems were fundamental. Building them required enormous amounts of expert time. Hours of interviews, manual coding of thousands of rules, painstaking validation. And the systems were brittle. They worked brilliantly within their precisely defined domains and failed catastrophically the moment they encountered anything outside those domains. They had no common sense, no ability to generalize, no capacity to handle the ambiguity and incompleteness of real-world information. By the late 1980s, the expert systems boom had become the expert systems bust. Companies that had invested heavily in AI infrastructure, custom hardware, specialized software, consultants, and developers found that the systems they had built could not be maintained, could not be extended, and could not deliver the promised returns. The market for AI hardware collapsed. Companies that had been valued in the hundreds of millions became worthless within years. The second AI winter was deeper than the first. And then, in the quiet years of the 1980s and early 1990s, while the mainstream AI research community was contracting, while funding was scarce and reputations were at risk, a small group of researchers kept working on neural networks. Geoffrey Hinton, Yann LeCun, Yoshua Bengio. They would eventually be called the godfathers of deep learning. They would eventually win the Turing Award, the highest honor in computer science. But in the 1980s, they were working in the margins of a field that had largely decided their approach was a dead end. Hinton, working at Carnegie Mellon and then the University of Toronto, was developing the theoretical foundations of what would eventually become backpropagation, the algorithm that allows neural networks to learn from their errors by propagating the signal of failure backward through the network, adjusting the weights of each connection to make the error slightly smaller next time. In plain English, Hinton was teaching machines how to learn from being wrong, the same fundamental insight that underpins every deep learning system that exists today. LeCun, working at AT&T Bell Labs, was applying these ideas to the problem of reading handwritten digits and building the convolutional neural networks that would eventually power every image recognition system in the world. Bengio, at the Université de Montréal, was working on the application of neural networks to language, laying groundwork that would eventually lead to the language models that now generate text, code, and conversation. Nobody was paying much attention. The field had seen too many promises. The AI winters had made funders cautious and institutions skeptical. The work that would eventually transform civilization was happening in relative obscurity, sustained by the stubbornness of a small group of researchers who believed that the combinatorial logic of deep neural networks pointed towards something real. The moment that changed everything, the end of the silent years, came in 2012. A team led by Geoffrey Hinton's graduate students Alex Krajewski and Ilya Sutskever submitted an entry to the ImageNet Large-Scale Visual Recognition Challenge, the annual competition that benchmarked progress in computer vision. Their system, called AlexNet, used deep convolutional neural networks trained on graphics processing units, GPUs, the chips originally designed for video games, to classify images. The results were not just better than the competition. They were so much better that the field effectively stopped arguing about whether deep learning worked and started asking how to use it. AlexNet achieved a top 5 error rate of 15.3%, compared to 26.2% for the second-place competitor. A gap so large that it was less like winning a competition and more like demonstrating that the competition had been in the wrong paradigm entirely. The silent years were over. Here is what the AI winters teach us. Not that failure is inevitable, not that ambition is dangerous, but that the relationship between failure and progress in complex technological domains is not linear. It is not a steady climb. It is a series of leaps, plateaus, and apparent retreats, where the retreats are not evidence that the project has failed, but evidence that the project has found the boundary of what the current approach can do. Every AI winter cleared away approaches that could not scale. Every abandoned laboratory freed up resources, human, financial, intellectual, for the approaches that could. The failures were not detours from the path to modern AI. They were the path. Researcher Yoshua Bengio, reflecting on the years when neural networks were considered a dead end, has said that the experience taught him something he considers essential: the importance of working on problems you believe are important, regardless of whether the community currently agrees with you. Because the community's current agreement is, at best, a snapshot of its current understanding, and understanding changes. This is the insight that matters most for anyone living in the age of AI. The systems you are interacting with today are not the endpoint. They are a snapshot. The approaches that seem most promising now will hit their walls. New approaches will emerge from the margins, from the researchers working in quiet, in funding scarcity, on problems that the mainstream considers solved or irrelevant or impossible. The next AI winter is coming, and it will build something we cannot yet imagine. Organizations like Pinnacle AI Solutions exist not just to help you use the AI tools that exist today, but to help you understand the deeper patterns of how AI evolves, how to distinguish between hype and genuine capability, how to build on what is solid and remain adaptable as the landscape shifts, how to be the kind of person and the kind of organization that benefits from change rather than being caught off guard by it. Because the silent years were not really silent. They were full of work, full of failure, full of the incremental, unglamorous, often unrewarded effort that makes breakthroughs possible. The question is not whether you will be present for the next transformation. You will be. The question is whether you will understand it well enough to use it. Every technology you use today was built on the wreckage of something that did not work. And the technology that will transform your world tomorrow is being built right now, in the margins, by people the mainstream has not yet noticed.